Today we explore an exotic phenomenon in quantum physics, the quantum capacitance effect, and its potential for revolutionary energy storage. In two-dimensional materials like graphene, electrons behave in ways that challenge our classical understanding of capacitance. Before diving into quantum effects, let's refresh our understanding of classical capacitance. In a classical capacitor, we have two parallel plates separated by a distance d. Positive charges accumulate on one plate, negative on the other. The classical capacitance equation, C equals epsilon 0 times epsilon r times area over distance. This is purely geometric. Notice something crucial. Classical capacitance depends only on the geometry of the plates and the dielectric material between them. It does not care about electronic properties. And charge stored equals capacitance times voltage. This fundamental relation still holds in quantum systems. For reference, a typical capacitor has capacitance around 1 microfarad per square centimeter. Keep this number in mind as we explore quantum effects. Now, what happens when we shrink down to atomic scales in two-dimensional materials? In materials like graphene, we have just a single atomic layer. The material is so thin that quantum mechanical effects dominate. Let me ask you a question. What makes two-dimensional materials special for capacitance? The answer lies in their electronic structure. The answer: in 2D materials, the density of electronic states becomes absolutely crucial. We cannot ignore quantum mechanics anymore. Graphene has a unique linear energy-momentum dispersion relation. Electrons behave like massless particles near the Dirac point, creating unusual electronic properties. Now comes the breakthrough. Quantum capacitance emerges from the electronic density of states. The quantum capacitance equation, C quantum equals electron charge squared times the density of states at the Fermi energy. This is fundamentally different from classical capacitance. Here, D of EF represents how many electronic states are available at the Fermi energy per unit area. For graphene specifically, the density of states equals 2 times absolute Fermi energy divided by pi times h bar Vf squared, where Vf is the Fermi velocity. Let's calculate a real example. For graphene with Fermi energy of 0.5 electron volts, the Fermi velocity in graphene is approximately 10 to the 6th meters per second, about 1/300th the speed of light. This gives us a density of states around 7.2 times 10 to the 13th states per electron volt per square centimeter. Converting to quantum capacitance, we get approximately 1.2 microfarads per square centimeter, remarkably similar to classical values, but fundamentally different in origin. In real devices, quantum and classical capacitances combine in series. The geometric capacitance and quantum capacitance act as capacitors in series, limiting the total capacitance. 1 over total capacitance equals 1 over geometric capacitance plus 1 over quantum capacitance. The smaller capacitance dominates. When quantum capacitance is small compared to geometric capacitance, it becomes the limiting factor. This is where quantum effects truly matter. Here's an important question. Can we actually tune the quantum capacitance? The answer is yes. We can tune quantum capacitance by applying a gate voltage, which shifts the Fermi energy and changes the density of states. This graph shows how quantum capacitance increases with Fermi energy. This tunability is the key to quantum capacitor applications. Now let's explore the energy storage implications of quantum capacitance. The energy stored in any capacitor is 1/2 CV squared. This remains true for quantum capacitors. Let's calculate the energy density for a practical graphene-based quantum capacitor. Assume total capacitance of 1 microfarad per square centimeter, limited by quantum capacitance, with a maximum voltage of about 2 volts before breakdown occurs. This gives an energy density of approximately 2 microjoules per square centimeter. Not impressive yet, but remember this is a single atomic layer. For comparison, lithium-ion batteries achieve about 0.5 joules per cc. The challenge is scaling up quantum capacitors. Can we actually build quantum batteries? Let's separate vision from reality. One approach is stacking many layers of two-dimensional materials, creating a layered quantum capacitor structure. Quantum capacitors offer several advantages: extremely fast charging, high power density, and electronic tunability. Charging timescales with RC, giving picosecond scale charging times. This is orders of magnitude faster than batteries. Power density can exceed 1 megawatt per kilogram, far surpassing conventional energy storage. However, significant challenges remain before quantum batteries become practical. Challenge 1. Energy density remains lower than conventional batteries. We need better materials or architectures. Challenge 2. Manufacturing high-quality two-dimensional materials at scale remains extremely difficult and expensive. Challenge 3. Two-dimensional materials can degrade when exposed to air, moisture, or mechanical stress. Let's explore some advanced concepts that make quantum capacitors even more interesting. Quantum confinement in ultra-thin materials creates discrete energy levels, leading to quantized capacitance values. The quantum capacitance becomes a sum over discrete energy levels. C quantum of n equals E squared times the sum of delta functions at each energy level. This quantum confinement creates step-like behavior, where capacitance jumps discontinuously as voltage changes and new energy levels become accessible. You might wonder, what about quantum entanglement? Can entangled states enhance energy storage? The answer: theoretical proposals suggest entanglement could provide advantages, but experimental proof remains elusive. This is cutting-edge research territory. While full quantum batteries remain futuristic, quantum capacitance effects are already being used today. Graphene supercapacitors are commercially available today using quantum capacitance effects to achieve high power density. Application 1. High-frequency electronics use quantum capacitors for ultrafast switching and signal processing. Application 2. Quantum capacitors excel at harvesting energy from rapid fluctuations, like vibrations or electromagnetic noise. Application 3. Neuromorphic computing chips use quantum capacitance for biomimetic synaptic behavior. The market for advanced capacitors, including quantum effects, is approximately $1 billion in 2024, growing rapidly. Different two-dimensional materials offer different quantum capacitance properties. Graphene shows linear Fermi energy dependence, molybdenum disulfide has constant density of states due to its bandgap, and phosphorine shows inverse square root dependence. Each material's unique quantum capacitance behavior makes it suitable for different applications. Molybdenum disulfide is better for logic devices because its bandgap allows switching between on and off states. Graphene excels in high-speed analog applications due to its high carrier mobility and zero bandgap. What are the ultimate theoretical limits of quantum capacitance energy storage? The maximum energy is the integral from 0 to maximum voltage of quantum capacitance times voltage times dV. Theoretical calculations suggest around 100 watt-hours per kilogram might be achievable with optimized designs. Van der Waals stacking of multiple two-dimensional layers could dramatically increase volumetric energy density. Future Direction 1. Heterostructures, combining different two-dimensional materials, could optimize both energy and power density. Future Direction 2. Topological materials with protected edge states might offer enhanced stability and unusual capacitance properties. Future Direction 3. Integration with quantum computing could enable energy storage that actively participates in quantum information processing. Realistic timeline: 5 to 10 years before we see practical quantum battery prototypes, 15 to 20 years for commercial products. Let's step back and appreciate the fundamental difference between quantum and classical capacitance. This represents a paradigm shift from geometry-dominated to electronics-dominated capacitance. It's a fundamentally new way to think about energy storage. In classical thinking, capacitance is a geometric property: bigger plates, smaller gaps, higher capacitance. In quantum thinking, capacitance becomes an electronic property: more available quantum states, higher capacitance. This opens entirely new design possibilities. We can engineer electronic structure rather than just geometry. Let's summarize the key concepts of quantum capacitance. Key point 1. Quantum capacitance emerges from the electronic density of states, not geometric factors. Key point 2. This effect becomes dominant in two-dimensional materials where quantum confinement is extreme. Key point 3. Quantum capacitors enable ultra-fast charge-discharge cycles, far exceeding battery speeds. Key point 4. The main current challenge is energy density, not power density. We need materials innovations. Remember this fundamental equation: quantum capacitance equals electron charge squared times density of states at Fermi energy. The quantum capacitance effect represents a revolution in how we think about and design energy storage devices. While fully practical quantum batteries remain 5 to 10 years away, the underlying physics is well understood and applications are emerging. The quantum capacitance effect beautifully bridges fundamental quantum physics with practical technology, showing how understanding nature at the smallest scales enables revolutionary applications.